Today in Algebra 2, Section 2.1, we are going to look at relations and functions. Relations can be represented many ways. Here we have ordered pairs, tables, graphs, and mapping diagrams. Okay, and they can be represented in ordered pairs. Remember, an ordered pair has an x value and a y value so that they can be plotted on a coordinate plane. Okay, in a table, it's the same thing. They just separate them out into rectangular boxes. On a graph, they take those ordered pairs and just plot them on the coordinate plane. So just like this ordered pair right here, -2, 2, and you have the same thing here, -2, 2, and if you put it on the coordinate plane, you have -2, 2 is here. Okay, a mapping diagram, they just put the x values or the input in the first column and the output or your y value in the second column, and you can see how the ordered pairs go from here. They just draw the arrows. Here you have -2, -2, and then you have -2, 2, 0, 1, and 3, 1. And you'll notice that in each set of these, no matter how it's represented, it gives you the same thing, the same answers, the same ordered pairs. Okay, in order for a relation to be a function, no x values can be repeated. So any set of ordered pairs can be a relation, but if we want to get more specific in that relation and call it a function, we have to look at the x values and make sure that the x value is not used more than once. In this first set of data, we have a graph, and we can get our ordered pairs from it. We have 3, 2 would be one ordered pair. -1, 3 is another ordered pair. 2, -4, and 4, -4. Okay, so when we look at these and we look at the x values, is this relation a function? Yes, it is, because when we look at these x values right here, none of them are repeated, therefore this is a function. However, when we look at the second set of data here, we have our x values in the left column and the y values in the right column, and we were to write those as ordered pairs, we would have -2, -4, we'd have 1, -1, and 1 is also paired with 2. And we don't even have to go any further because right there we see, okay, the x value was used twice. The same x value was used twice. So immediately we say, no, this is not a function. In a function, no x values may be repeated. That's important business right there. If you're looking at a graph and you want to know whether or not the graph is a function, if that relation is a function, you can do what's called the vertical line test. The vertical line test is just exactly that. The red line that they have here is what we're going to look at. If it doesn't cross the graph at more than one point, you're good. Then each x value is only used one time and it is a function. So you'll see if you were to take this red line here and move it all the way across, it would never intersect that parabola in more than one spot. However, when we look at the second graph, the parabola has been turned sideways. And so when you look at this vertical line, you can see that it passes through that graph at more than one point at a time. Therefore, the x values have been used twice, or the x values have been repeated. Therefore, this cannot be a function. Okay, let's look at these two equations here. The first one is y equals -2x minus 1, and the second one says f of x equals -2x minus 1. It's the same thing. One is written in xy notation, and the other one is written in function notation. Okay, here we have just an equation, a regular xy equation notation. Okay, here where it says f of x, that is function notation. All right, it means the same thing. It's like having a nickel or 5 pennies. It's the same value. Now, if we wanted to graph this, we would just make a table of values. We would have our x, which is our input or our independent or our domain, and we would come out with a y and output the range or the dependent variable. So if we put 0 in for x, we would get -1 for y. If we put -1 in for x, we would get an answer of 1. The y value would be 1. If we wanted to put 1 in for x, we would get -3. for our y. Okay, all of those are our ordered pairs, so we could graph those. At 0, we get -1. At -1, we get 1. And at 1, we get -3. You will see that those are linear. They fall in a line. Okay, if they fall in a line, that means that they are linear. Okay, the last question of the day for this assignment is the equation linear? Well, let's put a little English lesson in here. The base word of linear is line. Okay, so if the graph of this function makes a line, a straight line, then it's linear. If it makes anything else, it's not. Okay, so if we were to just put the y equals in our calculator, if we were to graph this, we would get a parabola that looks something like this. Is that making a line? No, it is not. If we were to put equation B in, g of x equals 5x plus 8, yes, we would get a straight line, therefore it would be linear. Okay, another clue is anytime you have an x squared, anytime there's an x squared in your equation, you're going to get a parabola. It is not going to be linear. You must have x to the 1 in your equation in order for it to make a line and be linear, but you can always just put it in your calculator and look at the graph and see whether or not it's linear. Okay, now if you have a function and it wants to, if the directions tell you to evaluate the function when x equals a number, so we're going to say to evaluate this when x equals -4, all that means is that we are going to substitute -4 in for x. So we would have g of x equals 5 times -4 plus 8, so that would equal -20 plus 8, and so that would equal -12. So another way that we could write that is that g of -4, we put -4 in for x, that's telling you what you're going to use for your x value. Then what comes out, we would get -12, and so actually that's just an ordered pair. When x is -4, y is -12, and that tells you that that is a point on that line of that equation, that function.